I want to talk about a research project that we are doing at dida, which is a joint research project together with a technical university in Munich, and more precisely the Chair of Remote Sensing Technology. And it's funded by the Bundesministerium für Wirtschaft und Klimaschutz. And the goal is to analyze and improve the applicability of AI methods for Earth observation. And I have the honor to present it here, but of course all the credit goes to the entire team. And at the moment, the core research team that is working on this is Joanna and Katja from TU Munich, and Simon and myself at dida. Let me start by introducing a little bit this field of Earth observation, which is a very broad field with many different applications, and in general it involves observing all kinds of different processes that happen on our planet Earth. Could be physical processes, chemical, biological. It's a really wide field. And applications are in, for example, agriculture, crop health mapping, or weather forecasting, climate research. It could be natural resource management, exploring mining sites, also disaster monitoring and response to them, forestry, and all the way to human infrastructure and monitoring urban growth, for example. So basically what I'm trying to say here, it's a really important and exciting field to be in, and every one of us has probably at some point come in contact with one of these applications directly or indirectly. For the sake of this talk and also for our research project, we of course have to narrow the scope quite significantly because this is just way too much. And what I want to talk about is a topic in agriculture, and it's a crop type classification problem from satellite imagery. And this brings me to another term that is associated quite often, comes together with Earth observation, which is remote sensing. And this includes all kinds of technologies that are used for observing the Earth, as the name says, remotely, which means that you don't really have to be on the location where you want to observe something. And it includes technologies like radar, LiDAR, aerial photography from drones or aircrafts, and as in our example, satellite imagery. And in particular, we are using multispectral satellite imagery. Let's talk a little bit more about this, the satellite data. It's maybe a bit hard to see here, but I've brought you an example. This is in an area of Berlin. We are currently somewhere pretty much in the center of this. This was taken earlier this year. And the satellite images are specified by three main different dimensions. It's the spatial resolution, temporal resolution, and the spectral resolution. Spatial resolution just means how much actual physical distance is represented by the pixels in the image. Temporal resolution is related to the so-called revisit period of satellites. Like when they orbit the Earth, it takes a while until the same satellite can observe the same spot on the Earth again. And spectral resolution relates to observing different parts of the electromagnetic spectrum. We are probably all familiar with the regular true color image that you can see on the top here, which has the standard red, green, and blue channel that we all know from digital photography. But satellites often also capture other parts of the electromagnetic spectrum, and most importantly, also infrared information, which is very useful to observe vegetation, for example. Just to give you a feeling for the numbers that we're dealing with here, we are using data from the Sentinel-2 program, which is a program by the European Space Agency and consists of 2 satellites, and they have roughly up to 10 meters spatial resolution per pixel, a revisit time of around 5 to 10 days, depending on where you are on the Earth, and 13 bands in the spectrum. So like the 3 red, green, blue standard channel, and then additional infrared, near infrared, and shortwave infrared. information. Generally, remote sensing data, and in particularly satellite data, is quite large in volume. So this Sentinel-2 program creates roughly 1.6 terabytes of raw data every single day. And it's also rather well accessible. So there's a lot of data products. There's free ones, there's commercial ones. And it's also, unfortunately, rather high dimensional and thus hard to interpret for humans. Not only due to the high dimensionality, but also because the underlying processes that we want to observe can be quite complex. But this makes it a perfect fit to do machine learning on this data now, because machine learning models are very good in processing and analyzing large amounts of complex data. Then this comes now with new challenges, of course, because most of the time you want to do supervised learning. And this means that you need labeled reference data. So satellite image alone is probably not enough to do something with it. This labeled reference data is much, much harder to get. It's much more limited in availability. And very often it has to be collected in situ by experts, meaning that there's really someone on the location. Cannot be collected remotely so easily. And also, it differs quite dramatically, the availability for different parts, different regions of the world. So we will later use reference data from the so-called Eurocrops dataset, which is, luckily for us, was already collected and prepared by another project of the group at TU Munich. And it contains basically the information of shapes of different agricultural parcels, like the coordinates where the parcels are, and also reports about what crops were grown in these parcels. And one reason why we have rather good chance of getting this type of data, even if it's still very time-consuming to collect and harmonize this across different countries, but we still have a chance to get this data in Europe, for example, because of reasons that agriculture is subsidized. And so the farmers have to report what they're growing, and so they have to collect this data anyways. For other parts of the world, it might be almost impossible to get this data. Even within Europe, the availability of data is quite imbalanced. So here we have an example from the Baltic states, Estonia and Latvia, where we have just much more data available than, for example, in Portugal. So this brings me then back to one of the main goals of our research, is the question, how can we leverage these larger amounts of data that we have to also help machine learning models on regions where we have less data, so transferring the knowledge between different regions of the world. In general, there might be other types of knowledge transfer that you could be interested in, besides just transferring between regions from one country to another. There might also be cases where you want to transfer knowledge between different classes, like you have trained a model that can classify different types of cereals. And then later you might decide, oh, now I want to also classify fruits and vegetables, and then you can transfer the knowledge that's already in the model and then improve on this later, the classifier. Or you can change the objective of the model, like first train a model that classifies land use, and then later you might decide, okay, now I want to use this information to improve a model that detects illegal mining activities, for example. Or lastly, transfer data that was collected on different types of sensors, different satellites. I will focus on the first two only in this talk, and these are very related because usually when you switch from one region to another, also the classes change because not all kinds of crops are grown in each region. So the first two always come together more or less. If we would follow a very traditional, we might even call it a bit naive approach now to to train on 2 different regions, we might first collect data on one region, train some learning algorithm, produce a model that solves a task for this region. And then we or someone else might collect data for a different region, use the same or similar learning algorithm, get a different model, and these 2 wouldn't have anything to do with each other. If we now realize, okay, for region B, maybe we don't have collected enough data, or the data is not high quality enough and the model really struggles to learn something on this region B, then in the naive setting where these 2 problems don't talk to each other would be, well, we have to collect more better data for region B, which is again very costly and time consuming. So a better way to do it is what I will be calling...
Sorry, closer to the mouth.
Okay. What will I be calling vanilla transfer learning? And here the idea is that we want to use the knowledge that is already contained in region A, or the model that was trained on region A, to improve the training process in region B. And the most straightforward way to do this is this pre-training fine-tuning approach, where you first train the model on region A and use that as a starting point to continue afterwards training on the data from region B. And this way, the model can still profit from something that it has already learned before. Now, another way to approach knowledge transfer is meta-learning. And here the setup is slightly different. The assumption here is that we have a collection of multiple different tasks that are not identical, but somewhat related. And each of them comes with their own separate data set. And you can train a model on them. In this context, it is called the base learning algorithm. And then the goal of the pre-training stage here is to learn about the learning itself. Right? So you have some meta-learning algorithm that observes the different learning processes on these different tasks and tries to gather some information about the learning itself from that. And the goal here is to then improve the learning algorithm itself so that it can more quickly adapt to new tasks afterwards. Right. So this might still sound a bit abstract for now. I will make it more concrete later, give you a precise example how we do this. But before I can do this, now might be maybe a good time to tell you a bit more about the actual problem that we try to solve and the data that we have for that. So as I said, it's crop type classification. And what we want to do is classify so-called crop phenology data. I will tell you on the next slide how we actually get to this from the satellite imagery. But the idea here is that phenology describes the growing stages of crops over a season, like in this case, it's always representing an entire year. And from this information, the machine learning model should decide what kind of crops is represented by this phenology data. And yeah, as I mentioned in the beginning, for humans, this might be a rather hard task. At least I cannot tell which is which here. I might be able to tell that they are different, but it's really, really hard to get some information out of this for human. Again, the crop type classification problem itself is rather important and has many different applications. Can be used for agricultural planning, keeping track of crop rotations, or targeted automated pest control, fertilization. Water management, like keeping track if, for example, in some region there's a lot of crops grown that require large amounts of water, or food security, economic planning, keeping track of supply and demand of different crop types. And as I mentioned before, in Europe, also the subsidy management plays an important role. So, not sure what you think about this, but for me, this definitely looks not like a satellite imagery. So what actually is this here? As I said, we start with this reference data that we have, which contains the shape in terms of coordinates for the different corners of the agricultural parcel. And using that information, we can now extract all the different tiles that a satellite has observed during the course of 1 year that contain this parcel, for example. And then each of these has these 13 spectral bands, so you get quite a few observations over the year of this same location. Now the next thing that we do is we get rid of the spatial dimension, and this has two reasons. First of all, we want to reduce the overall dimension. This is still a lot of data that we have to process here. And also, there's quite a bit of ambiguity in the size of the spatial dimension, because all shapes, all parcels have different shapes, different number of pixels that are contained in them, and makes it much easier for the machine learning model if we get rid of this ambiguity. So the common way to do this is so-called median aggregation. What this means is that for each of the time steps and for each of the spectral bands, we look at all the pixels that lie within the boundary of the parcel and just take the median value of that. And that gives us then 13 different values for each time step. And here you can see how this tracks over 1 year. And then the colors might be a bit hard to see, but here we have in there one line for the red, the blue and the green channel, and then all these shades of pink and purple are the infrared channels. So in summary, the entire problem then in the end becomes a multispectral, time series, multi-class classification problem. What kind of model do we use now to do that? For those that have been in the previous talk here, we also use a transformer model, but unlike the large language models, ours is not as large, so way smaller than the models that are usually used in modern text analysis. But the underlying principle is very similar. Instead of words, we have the different time steps. They are also embedded and combined with some temporal encoding that keeps track of which time step each of these embeddings belongs to. And then in these different transformer layers, I'm not going to go too much here into the technical detail, but there's alternating blocks that model interactions between the channels or the spectral bands and across the time steps, and keep repeating this a few times. In the end, you get some encoding vector for each time step, and all of these are aggregated and finally fed into a classification layer that results in scores for each of the different classes that we have in the dataset. For example, here, this input data belong to the class Barley. The most important part to remember from this slide is that we can split our model into two parts. The first we call the backbone, which includes everything up to the final classification layer. And then the classification head, which only includes this final classification layer. And the reason why this is a useful separation is that the backbone usually can be much more general and can contain information that is useful to different tasks, whereas the classification head has to be mostly adapted when we switch to a different region or have different classes in some new task. Okay. Now let me get back to the meta-learning. I promised you I would make it a bit more precise or less abstract, let's say. First, we have to now organize our data set to get these different tasks. And remember that what the model actually sees and learns from is this phenology data, but this is not so nice to look at. So I want to replace it with photos of the actual crops that it represents. But yeah, this is of course never seen by the model. So what we do first is we split our data set into different tasks that contain subsets of all the classes that we have. So for example, one task could be to classify apples against potatoes. One task could be classifying tomatoes against cherries, and so on. And what we follow here is a paradigm from few-shot learning called N-way K-shot learning, which means that now for each individual task, we have the usual split into a training and a test set. Only in this context, they are called support and query set, because training and test is already used to distinguish between collections of tasks that are seen by the meta-learning algorithm, right? So think about support and query as test and train and test set for individual tasks, and then meta-train and meta-test is collections of tasks that are seen by the meta-learning algorithm and where the meta-learning algorithm is evaluated. Now, n-way k-shot means that for each of these individual tasks, we will have n different classes per task, so in this case, 2. And k-shot means that we show the base algorithm that learns on a single task k examples per class in the support data set. So here k is equal to 5. Right, okay. This is the data that we use. And what we do in addition here in our case is, since we want to learn transfer between different regions, is that we attach each of these tasks to a sub-region of a certain country. So in this case, let's say we have collected a lot of data from the country Latvia, and then we split it into sub-regions, like similar to the states or Bundesländer in Germany. And then each task will only contain data samples belonging to some classes and come from one of these sub-regions. Okay. So this is the preparation, like this is how we split up the data. And now I need to tell you how we use this data. What algorithm are we actually using? And this is called the model agnostic meta-learning, or MAML. And model agnostic in this case means that it can be applied to all kinds of parametric machine learning models where the parameters are fit to the data in a like iterative gradient descent like optimization. So basically all kinds of neural networks, deep learning models, and in particular also our transformer model we train in this way. So the way that MAML works is for one of these different tasks, let's say apples against potatoes, we start our gradient descent optimization from some initial parameter values. So theta now always represents all the learnable parameters of the transformer model, and do some gradient descent on by using the support set, so the training data of that task. This is represented by the dashed line here. And at the location where we end up, we now evaluate this adapted model using the query set, so the test set of that task. And then the meta-learning algorithm asks the question by computing some gradients using the usual backpropagation things. Where should I move my starting position in order to make it easier for the model to adapt to this task? Like, where should I start next time if I want to learn quicker on this task? If we were only to classify apples against potatoes, this would be rather boring because we could just follow the dashed line. But we also have other tasks that we want to learn at the same time. And so we also do this same with tomatoes against cherries and so on. So then we get multiple different directions where we should move our initial parameters. And then the MAML algorithm tells us we should just take the average of all those directions and move the initial parameters in a direction that works best for all tasks on average. Right. So, and then you keep repeating this, and then the usual epoch-like learning. Now, I have one slide for all those that prefer formulas over illustrations. For those that don't like formulas, you might want to look away for one slide now. It's really not that important to understand the details here, but basically mathematically what's behind the meta-learning approach in this way is a bi-level optimization formulation. So you have this outer optimization that tries to minimize some loss function where we evaluate the task-adapted models on their query dataset, and the parameters for the task adaptation are subject to being the solutions of an inner optimization layer, inner optimization. And yeah, the notation is a bit vague here. What does minimizing near some value mean? So the idea is here, this is a non-convex problem. We might not exactly be able to solve it anyways and only move towards a local minimum. So this just tells us, well, we should optimize this in a way that we find a local solution, approximate a local solution near this starting point that we currently have. And MAML even tells us exactly how to do this by doing a fixed number of t gradient descent steps starting at theta 0. Okay. Those that looked away, you might look back now. There's one big downside to the MAML algorithm, which is the computational cost. So in order to solve this bi-level optimization problem, it requires computations of second-order derivatives. And this can become quite costly. So there's some variants of MAML that try to overcome this problem and reduce the computational cost. The first idea is called first-order MAML. And yeah, as the name says, it just tells us ignore all second-order derivatives, assume they are 0, and then solve the optimization problem that way. The anneal is almost no inner loop algorithm. This now comes back to this separation into a model backbone and classification head that I mentioned before. Anneal says, well, mostly the classification head will be responsible for adapting to the individual tasks. So why don't we just say during the task adaptation, so during all of these dashed lines, we completely freeze the backbone. We don't allow it to change, only update the classification head. And then only after aggregating these directions where we should move the initial parameters, theta 0, only then we allow the backbone to change as well. And yeah, this works quite well too usually. And it significantly reduces the computational cost. The last algorithm that I want to mention here is called task-informed meta-learning, TIML. This one does not decrease the computational complexity, but instead it's more specific to, let's say, geographic or Earth observation data, in the sense that it says, well, if we want to transfer knowledge between different regions, why don't we just add the location information, like latitude and longitude information of these different subregions or parcels? Why don't we just add this as additional input to the model? Then it might be easier to learn something about the regional dependency of all these tasks. And there's different variants of how you can do this. I don't want to go into the detail here. So there's different ways how you would integrate the latitude and longitude information into the model, for example. Okay, great. We do have a lot of different variants how we could approach transfer learning or like knowledge transfer now. How do we know which one to choose? Well, we benchmark it. We just try them all and see which ones is the best. So we have prepared a data set for that. Since it's based on this original Eurocrops reference data, we call our dataset now the Eurocrops ML dataset. And it, at the moment, we have benchmark information available for transferring from country Latvia to the country Estonia. So we start with some rather similar countries in terms of like similar climate, similar agricultural practices, probably also a lot of similar crop types. Not all of them will be equal, but there's quite a bit of overlap there. And then we check all of these different algorithms that I just introduced, how well they can transfer knowledge now from Latvia to Estonia. In Estonia, we have data for 127 crop types available. And in order to analyze the dependence of all these different algorithms on the amount of fine-tuning data that you give them, we now simulate different few-shot learning scenarios of different varying difficulties. So we artificially restrict the data that we give the algorithms during fine-tuning to only see like 1, 10, or 20 data examples per class during the fine-tuning. So this is some preliminary results that I can show you. As I mentioned in the beginning, this is still an ongoing research project. So we are still working on this. But what I mean by preliminary is not that I'm showing you results for unfinished experiments runs that have not converged yet. So all of these algorithms have been completely trained. What I mean is that there's, for example, different ways how you could fine-tune. You could use the same learning rate for the backbone and the classification head, or you could allow this to be different. You can tune the learning rate in different ways. As I mentioned, there's these different variants of TIML where we currently have only one of these in the results here yet. So there's no unfinished experiments in here, but we are doing more experiments in addition to that. So at the moment, this represents the fine-tuning scenario where we train the complete model, like backbone and classification head, using the same learning rate. So rather the simplest of the possibilities maybe. And what we can observe so far is that generally doing any kind of pre-training does help. So there is knowledge transfer from Latvia to Estonia, but it's not so clear which of the methods is the best. It's these meta-learning variants, especially MAML and ANIL, perform well when you have very little fine-tuning data, which makes sense because they were trained using this NVK shot setting before, where they also only see quite a few data samples per class usually, so they are used to these scenarios. Whereas the regular vanilla transfer learning becomes best if you have more fine-tuning data available, right? So last comment maybe about preliminary results. These are currently point estimates, so we've run all the experiments once, but especially in the low data regime where the algorithms only see one data sample per class, for example, the results can be a bit noisy, so we want to run these experiments several times and then report error bars on this basically, so also observe how sensitive each of these algorithms is to random effects. But yeah, this is still ongoing research, as I mentioned. Okay. We have done the first benchmarks on this data set, but even more so, we have published this data set. It's like everything that's contained in there is this combination of the reference data, like the shapes and labels, combined with the Sentinel-2 image tiles and these regional informations, all of that combined, doing this pre-processing step that I mentioned before, getting the crop phenology data, and then some more data cleaning. All of that we packaged as a freely available data set. Currently, it includes Estonia and Latvia. That is also our benchmark here. And we have also prepared already data for Portugal, so some country that is very far away within Europe. And the idea here is then to check how transfer between regions that are rather different in terms of climate and agricultural practices, and also the types of crop that are grown, how that would affect the knowledge transfer. If you're interested to check this out, we have code for using the data set within PyTorch with like datasets, data loaders ready. It's available on GitHub. It's documented, or you can just directly get the data on Zenodo if you prefer that. It's rather easy to get. Just pip install it and run our CLI download command. So yeah, we want to encourage everyone working in this field to do their own benchmarks if you have different algorithms in mind, because, well, we are limited by how many we can check in our benchmark. Yeah, so feel free to check this out. And then let me conclude. So what we have seen is that there's many different ways of how you can do pre-training and knowledge transfer between different geographical regions. And as far as we can say at the moment from our experiment analysis, the pre-training does help model performance, but it's not always clear which of these methods is the best. So roughly speaking, meta-learning works well when you have very little fine-tuning data. The regular transfer learning works better if you have a bit more data. But I should also mention that setting up all this meta-learning machinery, like with the different subsets, this N-way K-shot learning, is a bit more involved. And also these algorithms have usually more hyperparameters to tune. So it's all of that's a bit more complicated. So from my personal experience now doing this research project, I would mostly usually prefer to just do the regular transfer learning. Yeah, and then our next steps are, as I said, first incorporating this Portugal data to check how the knowledge transfer can be done between more distant regions. And then also a very interesting thing to look into is self-supervised learning. So here the idea is that you could pre-train a model backbone on the remote sensing data without the need for labeled data or reference data. And this will, of course, immensely help us to open up this large volume of remote sensing data that is available. And then only the labeled data and reference data would be needed for the specific fine-tuning task that you want to look into. So yeah, also we have that on the horizon to look into. Yeah, and with that, I want to thank you all very much.
We might have time for one question.
Thank you for the presentation. So standard images have 3 dimensions, RBG. And what would happen if you do the same project with standard satellite images? That's 3-dimensional. So is there a big advantage of using satellite images that have more dimensions? If this is the case, what are the other important dimensions of satellite images?
Yeah, so in terms of the general approach or the architecture, it wouldn't change that much, because if I go back to the model, the first thing we are doing is using this linear embedding layer to embed each of the time steps into some arbitrary dimension that is used by the transformer model. So only this first linear embedding layer would need to be changed if we had fewer channels down here. But then, of course, you lose all the information that was in these extra infrared channels, and especially for observing vegetation data, that is mostly what crop type classification is about. The infrared information is very important, contains a lot of useful information. So we haven't tried training the same model without all the infrared channels, but I would assume that it performs way worse.